Hello, everybody. This is Dr. Flight, and this is going to be a lecture video demonstration on logistical regression in SPSS. What we have here is a data set that it's labeled class grade data, and what it is a series of students listed. There are 104 students total. So we go down, we see 104 cases, and these students have grades that are identified here by different types of grades, and one is a case analysis, one is a homework average. There are 3 different tests, and then there's a paper. So these are percentages that the students received on these various items. And then what we have here under just simply labeled class is a 1 or a 0, and 1 indicates that the student received either an A or a B in the course, and a 0 indicates that the student received a C or below. So these are A's and B's versus C and below demarkers for student performance. And so what we want to do is we want to create a model that will predict classification of future students, and we want to be able to identify which students will be in the A-B group and which will not. It would be nice to know if these these assignment types, or these individual grading elements here, if any one was more significant than another, or if there are some that are not significant at all. So the first thing that we would do, or that you should think about doing, is again going through your data and identifying outliers, and also identifying whether there's multi-collinearity among these variables. So if we go to Analyze and then we go to Correlate bivariate, and then if we track down and take our 6 independent variables here, which would be the different forms of assessment for each student, and we go OK, we can take a look at the correlation matrix. And when we look at this, what we're looking for are variables that correlate with each other at something fairly high, like something probably above 0.7. So we have test 3 and test 1 that correlate at 5.5. We have test 2 and test 3 that correlate at 0.6. 1 and 2 correlate. So the tests correlate with each other, although we'd probably expect that, and none of them correlate above 0.7. So my guess is there's probably not a lot of collinearity going on here. But we could actually do this in a regression. We could actually do this just to look at this. Go to linear regression. And then what we're going to do is we're going to put in our dependent variable. Now this is interesting because all we're doing is testing for multi-collinearity. I know we're running a linear regression, but we're only using this tool to be able to look at the multi-collinearity if there is any. So with this here, we want to look at collinearity diagnostics. And we really don't want a model estimate, and we really don't care what it fits like, because that's not really what we're running this regression for. That's not the purpose. The purpose is to look at the collinearity that's going on there. We could look at the plots and some things like that, but really let's just do this one little thing. We're going to look at this box in the VIFs and tolerance. Remember, as we do this, we are concerned with, and we're thinking about, tolerances above 0.1 is what we want, and we want VIFs below 10. That's what we want, and clearly there's no problem here. So it doesn't look like collinearity is an issue at all moving forward. Please note you also want to look for outliers, potential outliers here as well. So we could do that, and you would want to do that anyways with any type of research that you're doing. But to get on to this logistic regression, this is going to be a binary logistic regression because we've got one term, one dependent variable that we're looking at, and I actually had some data already in here, or the variables already in here. So we have the class, and this regression now we are running because we do want to specify the model. We want to get the actual coefficients, the logits for each for each independent variable here, and we want to move forward. So we've got this in here. Just to note, and I'm sure you've either seen or heard this before, if any one of these independent variables are categorical, if any are categorical, you need to go into this tab here, the categorical tab, and you need to input your categorical data here. And when you do, it'll ask you which level of your categorical variable do you want to have or serve as your base or benchmark level. So that's something in regression when you have a metric variable with multiple levels, you need, and it's not a dummy variable, non-metric variable that's not a dummy variable, you need to specify the benchmark level because that's the level that will not be estimated. Okay, so anyways, we do not have any categorical covariates. All of ours are metric, so these are the independent variables that they're all metric, and we think these predict which classification a student should be placed in either the A, B group or the C or below group. So that's what we're going to do there. Other things that we can look at when we go to the save option, we may want to save probabilities and or group membership. So probabilities and group membership, I'm going to click those so we can look at those. This is the predicted group that the model will say an individual should drop into and the probability that that person would be in that group. So we're going to do that. We're going to do options. Now under options here, a couple things. The Hosmer-Lemeshow goodness of fit, that's something we can report. That's a reportable figure, so that's good. We want that. We have an opportunity here to look at outliers. If you have not examined outliers already, here's a chance for you to specify those. And the default is a 2 standard deviation position. The confidence interval is nice to have. Some folks will check the iteration history if you want, especially if you're using some type of a stepwise, either a forward or backward entry method of variable entry. That can be done. Also, I just want to point out the cutoff point. So you can specify the cutoff point. Now, remember, a probability will be created for each case, and it'll be between 0 and 1. That'll be the probability. It'll be between 0 and 1. And what this is saying is that anybody whose probability is calculated above 0.5 will be in the first group. Anybody whose probability is below 0.5 will be in the second group, because they're not in the first. So 0.5 is the designation of the probability of the point in which we classify a person falling in one group versus a person falling in a different group. So that's this 0.5 right in there to be just so you know that that's there to specify. Okay, so we're going to run the regression. We're going to hit okie dokie, and we're going to see what pops out here for our model. Now, we have our case processing summary. We had 104 respondents. We did not take any out for missing data. We have the coding. So anybody who's an A or a B is coded as a 1. And anybody who's below a B is a 0, and we know that from the data that we inputted. So that's cool. This is a very important box. This is the base model box. So I think I used an entry method, if I remember correctly, on here. So all the variables are going to be entered in, and and or I might have used a stepwise regression. I can't remember, or a forward walled is probably, it might have been what I used. We'll try a couple different things though. But this box here, classification table, what this says is basically if I took my 104 respondents and I put them all in one box, so I said all of them are A's or B's. So all 104, you all go in the A-B category, then I would have been correct 61% of the time. It's because 61.5% of the respondents were A-B's. So at the very worst, the absolute very worst, I should be able to predict 61% of these cases. And that is if I just took all of them and put them into one box, the A-B box. So this is the baseline model, and basically the idea is when we use independent variables to predict class membership, we want them to be able to do better than 61%. And if they do, then we could say that the model is good, I guess, at predicting group membership, or at least it's better than the base. So, so that is what the test will be to know whether we have a good model or not. It's whether it's whether the model better predicts than chance, if you will, or just a baseline estimate. Okay, so 61.5, that's important to remember. Okay, this first entry, it's a block 0, it's actually block 0. So this is before a regression is run or before things are technically estimated. Basically what happens is initially what the data will be run, and what this will say is if I didn't have any data, I would have a constant, or if I didn't have any independent variables, I would have a constant and I would have everything excluded. This is not particularly interesting, except that you may glean a little bit of information from these variables here. Like, so for instance, homework may be something that is significant, maybe not, maybe one of these tests would be, but we need to do further analysis. Okay, so then we get into the actual model estimations. And in this case, we're only doing, it looks like there's one block and it looks like there's one step in this block. So this is a model that was fitted pretty quickly without a lot of, kind of going back and forth. Now, this is an enter model. So all the variables are entered together, and we'll run it again using a forward entry method, kind of like stepwise regression would do. Okay, so in this model here, this Omnibus Test box indicates that the model that we have created is significant in that it better predicts above and beyond the base model in terms of how predictable it is, or how well it predicts case entry, case placement. So this is one indicator that our model will be significant, and we have 0.003 and a chi-square test that suggests that this model that we have will be significantly better than a baseline model. But we're not going to worry about or report that right now. The next box, this is the -2 LL. This is the log likelihood, which if there were multiple steps here happening, or multiple blocks and steps happening, this number would actually go down, which is good, and these guys would go up. So the Nagelkirk R-square and the Cox-Snell R-square are literally the like in a regression, the coefficient of determination, the R squared. The one we want to report is the Nagelkirk R square for logistic regression. Okay, so 0.239. Now, 0.239 may not sound super good, but it's not bad. In a Logit model, it would be significant, and it is significant in this model. So 0.239 is our R squared that we will report. The Hosmer-Lemeshow test is another approach to a chi-square test for the model. Okay, so remember above here we had 0.003 and we said that that would be significant for the Omnibus test. For the Hosmer-Lemeshow test, we reverse this. So this is a reverse interpretation, and anything above 0.05 is significant. Here we have 0.876. So clearly this model that is being created will better predict group membership than the base model did that we looked at before. Okay, so that's the Hosmer-Lemeshow. We report that. We report our R squared. Moving forward, the contingency table. Now this is kind of an interesting little box. What this does is it actually, again, helps indicate how well our predicted model classifies individuals. So what we do here is it will do a series of steps where it takes small groups of respondents and classifies them, and then it looks to see how well it classifies them. So like it took 10, like the bottom line here, you look at the bottom, it took 10 groups, and there were, on average here, out of the 10 groups, it would have expected 1.7 respondents to be in class below B, and the actual result was 2, and it would have expected 12.27 to be in A or B, and the actual result was 12. These numbers, 12 and 12.27, are super close, and the 2 and 1.7 are super close, which means that the model is predicting reality fairly well in small groups, in small batches. So again, this is it's a result of the Hosmer-Lemeshow test, but it's kind of like a simulation, if you will. And again, it's, as a researcher, it's just further evidence that the model's predicting what it should. It's okay. It may not be reportable. You're not reporting that necessarily, but that's again your background information. Now, this classification table is reportable and is very important. So remember before, if we cruise back up to the top here, remember in block 0 that before we even began, we had first classification table. In block 0, we had 61.5% of our respondents being identified properly, and that was only because we put everybody in the same block, in the same class. And I said that we wanted to do something better than 61.5%. Now we come back to the classification table and we look at how well the model classified the respondents relative to the actual data. So what it did was it predicted that 19 would be in B, and 20, or it predicted that 19 would be, 19 would be here, and 10 would be here, versus what was observed. What was observed here. And I'm not sure I'm getting that quite right, but the bottom line is it predicted the below B group 47% of the time, and it predicted entry into the A or B group 84% of the time. So in other words, roughly half the time, 47% of the time, it correctly predicted the C or below group, and in roughly 84% of the time, it correctly predicted the A and B group, for a total prediction average of 70%. So remember, our benchmark was 61.5, so we're doing well better than our benchmark in order to predict what we, who should go where. Okay, so that's why this model is significantly better than the base model, because of that difference right there. And that you want to report. So this model's predicting group membership 9%, roughly 9% better than, actually 8.7% better or something like that, than the base model. Now, moving forward, the very last box, so we have one case that may be an outlier, but beyond that, this last box here is the one where we look at significance among these independent variables. So the beta, the B here, this is actually the logit that we use, and this is the column. This column here is used to actually create the variate. If you remember, there's a G sub x formula. The G sub x formula is the one that we look at for the for creating the predictive model. We have a constant, and then we have these numbers here. Now, some of these we may not use because they're not significant. So case, it looks like it would, and let me add that these significance levels can be a little soft. So 0.075 we would use. We would use that in the model. We would not use homework. We would not use test 1, test 2. We would use test 3. We would not use paper probably, and we would use the constant. So in other words, out of these 6 items, case and test 3 are valuable in predicting this model, and those would be the ones that we would use and that we would interpret. So the beta then is the logit, is the predictive weight that's used in the G sub x formula. Now, when you take the G sub x, what you actually do is use that to help create this exponential b. So you take the natural, the e value, the e log, so it's like the natural log raised, or the e, and then this log here, and you come up with this value. This is super important, and you probably looked at this before, but what it basically means is that if somebody improves in their case score, it has an impact of 41 times the weight in placing them in the A or B group. So if the students do well in cases, they're 41 times more likely to be in an A and a B group, the A-B group. On test 3, so this is a very important test. Test 3, if the students who do better on test 3 have a 73 times as likely to be in the A-B group than somebody who doesn't do well. That's how these exponential, they're not exponential, but they are. It's like the natural log raised of B here in this. So it's the E. So that's how that reads. Now, this is very cluttered, admittedly, because we did an enter version of the test, so all of our variables are in here. Let's take, for instance, if we do, let's do analyze regression, binary logistic, but let's change our method of entry here. So let's not just do this. Let's do the forward walled, and what it'll do is it'll add variables throughout the process. And we're going to do OK. So we got the logistic. We got the same information we had before, because we're not changing the same first block entry. Nothing has changed here. So it's basically like the null model that you're looking at when we look at block 0. And that's what we're looking at things against. Now, when we did the stepwise, the forward walled, and the walled is the test that allows the variables to move forward. We have 2 steps, and we have This, again, Omnibus Test, again, is significant, which we knew it would be. But what it does is it helps us better understand how it helps us understand how well the overall fit is. We have, and again, for instance, down here, corresponding to the Omnibus, the Hosmer-Lemeshow test, again, 0.789, that corresponds with the significance level. Now, interestingly, you'll notice that the R-squared finishes at 0.214. This is going to be a little bit below what we had before. And what's going to happen is we're not going to have in the final model all the variables, all 6 variables. We're only going to probably have 2 variables and the constant. So when we lose the other 4 variables, we lose a little bit of R squared, but we're willing to give that up for the parsimony of the test or of the model. When we're going from 6 IVs down to 2, we're naturally going to lose some R squared, but the variables we're losing don't predict much in the model anyways. So that's kind of what's going on with that. All right, so everything is looking good here. The contingency table, again, we run 2 of them because we're doing a stepwise type of a entry method. So we had 2 steps that happened. So we have 2 runs of the contingency model. This bottom one was the one that was accepted. So step 2, this second model, step 2 model, is the one that was finally accepted, and that would be the best fitting model given the variables that we have. This model actually, because of the method that we used and we eliminated some of the bad variables, what improved the percentage correct. So we actually have a better percentage now. We have 75% of our model being predicted as opposed to our baseline of 61.5%. So this is fantastic. This is outstanding. This is a good, big jump in terms of predictive ability between our models and between the base model and what we have here. So variables in the equation, again, we're looking at step 2 because that was the second regression or the second variant that was used. It has, interestingly, we have case and we have test and we have constant. So like we did in the entry version, we noticed that case and test were the significant variables. Here they are again with the other variables dropped out. And this is the true thing here. When we look at this, this is really important. When we look at the influence that these variables have on placing someone in the AB group, people who improve and get better at the cases are 67 times more likely, almost 68 times more likely to be an AB student. People who do well on test 3 are 160 times likely to be an AB student. So that is like really telling in terms of what is significant for a student to focus on maybe during their time in this particular class to get a good grade. Okay, so now the rest of the analysis, this talks about the variables that were dropped and whether they were significant or not, and they were not, but we knew that already. So these are the 4 variables: homework, test 1, test 2, and the paper. And then based on this data, without these, there is no respondent that is an outlier in this particular data set. Okay, so moving here, this 4.2, this 5.0, and this negative 6.8, these are our these go into the variant. These are our logits, the predictors that we would use in our analysis. And then finally, this is how we can interpret them. Now, let me also say this. If one of these is negative, like if test 3 was a negative, then what that would mean is that it per times is the increase in likelihood that it would be in the group 0, which would be the C or below group, as opposed to the A and B group. We don't have that here. That's not the case. But if one of these was negative, it contributes to the likelihood of the opposite group, and that's how that's interpreted. Now, one other thing before we wrap this up. We had these variables here that were added. Now, we ran this model twice. These two variables were added with the enter model. These two variables were added with the last model, which was the forward walled model. One is the percentage, and the other is the grouping. Now, if we look down here and we look at these groupings, we remember the cutoff was a probability, and basically what's happening is you take the let me see if I can do this real quick. This information here, the case, the 4.2 and the 5.0 and the -6.8, these are used as a formula G sub x, and the G sub x formula here creates the function, the G sub x function. Then we use the G sub x function as in the formula in a second function to create P sub x. Remember the pi sub x, the P sub x? Well, this column is P sub x for each individual variable or each individual respondent. So we have a P sub x, which is the probability that's created. And we remember the cutoff value, 0.5. Okay, so anybody above 0.5 in this column should be a 1. Anybody below 0.5 should be a 0. So if we scroll down here, we're looking at all, we have one here. We have one here. These are zeros. These are below 0.5. This guy's above 0.5, barely, but they are nonetheless, because that was our cutoff point for this. So we have cutoffs that are accurately hitting below 0.5. Now, if something was skewed in the data, and you noticed this, if there was an oddity in the data, you can alter your cutoff point. We could have made the cutoff point 0.6 or 0.4 or whatever. It didn't have to be 0.5, but that's the norm, and that's kind of the expectation to start with at least. So it may actually be, you might actually be able to create a slightly better predictive model if the data is skewed somehow to where you can create a model and go from there. Now, I'm not going to do this, but if we looked at this predictive group and we looked at the actual group, we could probably run a correlation, and those would be right. I don't think they would be right, the correct percentage, because what we're saying is 75% of the time we should be correct in this. So we could actually probably test that again. I'm not going to, because we already ran the analysis. So anyways, this is a walkthrough in a Logit model run predicting group membership for students who are receiving grades in a class. And we found, interestingly enough, that the casework that they did and the work they did on test 3 were most significant in predicting group membership, and we found out the times in which they were significant and so forth. So if you have any questions, feel free to touch base, and I thank you for listening to and thinking about this topic.